Hi everybody, this video is going over the Unit 1 practice exam for Physics 251. Number 1, a diver stands on a diving board, bounces to create an oscillation, then swan dives into a swimming pool. Draw a motion diagram for the diver after they leave the diving board. Use 6 to 8 dots and sketch in appropriate velocity vectors. Graphically calculate the magnitude and direction of the acceleration vector at the highest point in the diver's trajectory. Okay, so if the diver is behaving as a projectile after they leave the diving board, that means first we don't have to consider any of the oscillations that it took in order to get the diver into a place where they could behave like a projectile. And two, when they are moving like a projectile, we know that the acceleration in the x direction is going to be equal to 0. The acceleration in the y direction is going to be consistent, so that on the way up, the y components of the velocity shrink at a consistent rate. On the way down, the y components of the velocity grow at that same consistent rate. So I started with time 0 here, and I arbitrarily chose a horizontal velocity component of 6 blocks to the right, just so that I could maintain that as I continued making velocity vectors. I also arbitrarily chose to make the initial vertical component of the velocity 6 blocks high, so that I could subtract from that at a consistent rate on the way up, and then add to that consistently on the way down. So because I have 7 times or 7 dots, I'm going to end up with a total of 6 velocity vectors because I have 6 intervals. And velocity vector v0 is the one that's going to start at time 0. I don't have a v6 vector here because my last interval is actually v5. But I've color-coded so that the horizontal velocity vectors do not change their length at all. The vertical ones shrink or grow by the same amount each interval. So v0x here, starting at time 0, is 6 blocks high. I arbitrarily chose to just subtract 2 blocks off for each interval, and then I needed to add 2 blocks once I got past the apex of the diver's motion. At the highest point in the trajectory, I am going to take the vectors bounding either side of that, so v3 and then negative v2, and I can add those together. So I need a negative sign right here for v2, but what we're going to find is that the horizontal component of v3 cancels the horizontal component of v2, but the vertical components don't cancel, and they're going to end up pointing down because we know it's Earth that's influencing the diver once they actually leave the diving board. And the direction of that delta v vector has to be the same as the direction of the acceleration vector, because acceleration is the delta v vector divided by delta t. And delta t is always going to be a positive, so it's not going to have the ability to change the direction of the acceleration vector. That always has to be the same as the delta v vector. Number 2 is a velocity versus time graph. We have an object that's moving for 15 seconds, but it is not maintaining one constant velocity for those entire 15 seconds. It's undergoing some changes in its motion. I need to figure out where it is at t is equal to 15 seconds. And note, it's crucial that I know where this object began, because the initial position on the x-axis is not something I'm going to be able to get from this velocity graph. There's more than one way to solve this. The first way is to break this graph up into sections that all have consistent slope, and then I can compute the slope of that velocity graph, which has to give me an acceleration. That acceleration is something that I can plug into a kinematic equation. So for the first interval from 0 to 5 seconds, the initial velocity is 0 meters, the final velocity is 5 meters, and I know my time interval is 5 seconds long. That means the acceleration is 1 meter per second squared. I can go to the first kinematic equation, the one for position, and I know I'm dealing with an object that's moving on the x-axis. So those initial s's can be turned into x's. X initial is given to us, that's 0 meters. V initial x and delta t I can read off the graph, and I calculated an acceleration of 1 meter per second squared. So that's going to leave me with 0 meters plus 0 meters plus 12.5. So that tells me that at t is equal to 5 seconds, this object has moved from 0 meters to positive 12.5 meters. Now from 5 to 10, I have a horizontal section, and that means something different on a velocity graph than it means on a position graph or an acceleration graph. Here, I know this object is just maintaining a constant velocity of 5 meters per second for 5 seconds. So that tells me that my delta v vector up here in the numerator of the acceleration equation, that's got to give me a 0, because time is still moving, but the velocity is not changing. So 0 meters per second is the acceleration. I can take the final position from the previous step and make that the initial position in the next step. And I don't have to change the equation I'm using either. The same one will work for all steps of this problem. Now I plug in a 0 for the acceleration. I get 12.5 meters plus 25 meters plus 0 meters. So that's the amount of time that this object spends, or I guess really the amount of distance that this object adds as a result of just moving 5 meters per second for 5 seconds, but without changing velocity. Now for our middle step here from 10 to 12.5 seconds, if we take a look at this, the slope does not actually change at 12.5 seconds, but something about what this object is doing changes at 12.5 seconds. So I've got a new slope to calculate, -2 meters per second squared. I can take the final position from my previous example, and I can make that the initial position of this step. And I can take the initial velocity at 10 seconds, which is still positive 5 meters per second. And what I find is that at 12.5 seconds, this object is at a position 43.75 meters. From 12.5 to 15 seconds, the slope is no different. So when I take a new v initial and a new v final, I don't get a different number than I got for the previous section. I do need to take the final position from the previous step, make that the initial position in this step. And now I'm just looking at what this object is doing from 12.5 seconds to 15 seconds. And at 12.5 seconds, it's crossing the x-axis. So that means that instantaneously that object is at rest. So I end up with 43.75 plus 0 meters minus 6.25 meters. I get right back to 37.5 meters. So that tells me that this object reaches its final horizontal position at t is equal to 10 seconds, but it moves forward and then backward by exactly the same amount. So note, I mentioned that that was just one way that you could solve this problem. The other one is to compute some integrals, because I have a series of rectangles and triangles in the area below this curve. I'm just bounding this curve to the x-axis, so I don't need to consider anything in the latter portion or the bottom portion of this graph, just this triangle, this rectangle, and then these two triangles I have labeled 3 and 4. So because I have a velocity graph, if I compute the area below the curve, I'm going to end up with a displacement. And we can see that here by just taking the area of a triangle. So 1/2 base times height. This particular triangle has a base of 5 seconds, a height of 5 meters per second. So that ends up giving me 12.5 meters, which is exactly the same answer that we got using method 1. Next, for section 2, I have a rectangle that's 5 seconds wide, 5 meters per second tall. So when I multiply those, that's 25 meters of additional distance that I'm adding to this story. And if we look at triangles 3 and 4, the ones that go from 10 to 12.5 seconds and then 12.5 seconds to 15 seconds respectively, those triangles have the same area. The only difference is that one of them is below the x-axis and one is above. So I end up with an additional 6.25 meters added to the position, and then the same 6.25 meters subtracted off. And the difference between doing it in method 1 and doing it with method 2 here is that there's one additional step in method 2. I have to add all those individual displacements together so that I get 37.5 meters, just like we saw with our last example. Number 3 is a vector question. We've got 3 vectors, A, B, and C. They're written out here in unit vector notation, but as we're going to see, that is not the only way that we can understand what information is embedded in these vectors. I need to find vector D, which is 5 times the quantity A plus B minus 2 times C. So using the order of operations, I'm going to start with adding A and B together so that I can just take the X components, 3.6 and negative 1.7 to get my I hat component of 1.9. Do the same thing with your J hats, you get 7.1 J hat. So if I need to multiply that vector A plus B by the scalar 5, all I'm doing is individually scaling each one of those components up by a factor of 5. So 5 times 1.9 yields 9.5. 5 times 7.1 yields 35.5. Moving on, I know that I'm subtracting 2 times vector C, not just vector C itself. And because I'm ultimately going to be subtracting this, I'm going to take care of 2 steps in one by just multiplying vector C by negative 2. So negative 8.0 becomes negative 1.6 in the I hat direction, and negative 9.0 becomes positive 18 in the J hat direction. Therefore, I can add my first vector, which is 5 times the quantity A plus B, to my second one, which is negative 2 times vector C. I get 11.1 I hat plus 53.5 J hat. And now is the appropriate time to use sig figs because I do have 2 with this problem. So that D vector becomes 11 I hat plus 54 J hat. Now, we're not done because we also need to get the magnitude and direction for vector D. And all I need to do in order to calculate the magnitude is to take the X component, square that, add it to the square of the Y component, and then take a square root. And I'm reverting back to my unrounded values for this. So squaring 11.1 and adding it to the square of 53.5 gives me 2,985.46. If I take a square root, that's 54.6, so 55 to 2 sig figs. And the units I've just left as generic units here. This doesn't necessarily represent a group of position vectors or velocity vectors or acceleration vectors. So 55 units is sufficient to tell us what its magnitude is. Because both the X and the Y components are positive, I know vector D is going to live in quadrant 1. So I can plot vector D in quadrant 1 and then just decompose it so that I can project the dx vector onto the x-axis and the dy vector onto the y-axis. And I'm choosing to give this angle with respect to the positive x-axis. So when I use the inverse tangent, the opposite is going to be dy. The adjacent is going to be dx. So I end up with an angle of 78.279 degrees, which to 2 sig figs is 78 degrees. However, there's no reason whatsoever that I couldn't use an angle that is expressed with respect to the y-axis. I would just end up with the complement of this angle because the ratio that's inside of this inverse tangent would now inverse. So the opposite and the adjacent would take each other's places. Four is also a vector question, but now this is one that I can tie to the maneuvers of a drone. So I've got 4 different maneuvers. I'm going to indicate those with vectors R1, R2, R3, and R4. Since this is involving 3-dimensional motion, I need to add a k-hat unit vector to each one of these maneuvers. This first one is 3.0 meters straight up, so that's along the z-axis. That means in the I hat and j hat directions, these component vectors are going to be 0, but in the z hat or the z direction, I have 3.0 k hat. Vector 2 is 2.6 meters directed 28 degrees south of west. And with these cardinal directions, I can correlate these to Cartesian coordinates, where south would just be like the negative y direction, and then west would be the negative x direction. So to determine what vector R2 looks like, I suggest you sketch it, where you start with the western direction, so the negative x-axis, and then you sweep towards south by 28 degrees. That gives me a vector that is in quadrant number 3, so both the x and the y components are negative, and that's 2.6 cosine 28, negative 2.6 cosine 28 for the I hat direction, negative 2.6 sine 28 for the j hat direction, but this maneuver is not including any movement on the z-axis. So I'm just going to add a plus 0 k hat there just to complete that vector. For vector R3, now we're drawing 7.3 meters directed 19 degrees east of north. So I'll start in the north direction, which is like positive y, sweep toward the east, which is positive x, and the right triangle that I build out of that is going to have a hypotenuse that's 7.3 meters in magnitude. And if I break this down into components, I get a positive for the I hat direction and a positive for the j hat direction. Still no motion in the k hat direction. So the second two maneuvers do not actually bring the drone closer to the ground or further from it. I do want to call attention to the fact that it is not safe to assume that every x component is going to be a cosine, every y component is going to be a sine. And we can see that really clearly here with vector R3 because the adjacent piece of this right triangle points in the y direction. So that's why I have a cosine with my j hat unit vector. And then finally, maneuver 4 is pretty simple, 4.5 meters due east. So that's in the positive x direction. So that's just 4.5 I hat plus 0 j hat plus 0 k hat. And the easiest way to make a mistake on this question is with defining vectors R2 and R3. Now that we've got those, we can just take all of the x components together. So I'm going to add 0 to negative 2.6 cosine 28 to 7.3 sine 19 to 4.5. And if I do the same process for the other two directions, I find that nothing really interesting happens in the z direction because there's only that one maneuver that brings the drone closer to the ground or further from it. And in the x direction, my component's positive 4.581. It is positive 5.682 in the y direction. So to find the magnitude, I can square each of those components, add them together, take a square root. What I'm left with is 7.8909 meters, and here it's appropriate to apply sig figs. So 2 sig figs takes us to 7.9 meters. Peregrine falcon flies in a straight line that can be described with the following position function. So this is our generic s-axis again. S as a function of t is equal to 6.8 meters minus 1.7 meters per second squared times t squared plus 0.25 meters per second to the fourth times t to the fourth. So those units in the last term in particular, that's different than what we normally see with a position function. But what we find that we're going to be able to do is that when we plug in the times, so 3.0 second for each of these examples, that's going to affect the units that are inside of the parentheses for anything that's multiplied by a t. For part A, we're just concerned with the falcon's position. So we don't need to manipulate that function any further. We just need to plug in t is equal to 3.0 seconds. And doing so now converts or changes all of the units in the statement to meters. I have 6.8 meters minus 15.3 meters plus an additional 20.25 meters. I get 11.75 meters, but we have 2 sig figs on this problem, so that becomes 12 meters. And to answer B and C, I need to take derivatives. So one derivative of the position function is going to give me a velocity function. So v as a function of t is equal to s prime of t. That is 1.7 meters per second squared. And this t squared now means I need to multiply 2 times t to the first power. The t to the fourth in the last term means that I'm multiplying 4 times t cubed. And my velocity function is shown here on the second line, minus 3.45 meters per second squared times t, plus 1.0 meters per second to the fourth, times t cubed. And when I plug in the time, 3.0 seconds, one of the seconds that's present in the numerator of the acceleration term here gets canceled, but not both of them. So I still have meters per second here, and I end up with meters per second in that last term as well. So negative 10.2 plus 27 gives me 16.8 meters per second to 2 sig figs, that is 17 meters per second. And then finally for the acceleration, I have one more derivative of the velocity function, so that I end up with negative 3.4 meters per second squared times 3.0 meters per second to the fourth times t squared. If I plug in 3.0 for t, there's no change to the first term in this expression, but 3.0 meters per second to the fourth times 3.0 seconds squared, and that's a 2. That just looks a little odd. I'm going to end up with acceleration units I'm adding together. So 23.6 meters per second squared rounds to 24 meters per second squared when we apply the appropriate sig figs. Verse 6, we have a cyclist that begins at rest. They accelerate at a known rate for a known time. They then maintain that velocity for a different time and then quickly apply the brakes so that they can come to rest. In order to set this up, we have to recognize when the acceleration is positive, when it's negative, and when it's 0. And because our cyclist is going to be moving forward, if those velocities are positive, then combining that with a positive acceleration tells us that the cyclist here is going to speed up from rest. So from 0 meters per second to some v final that we can calculate just by using our kinematic equations. So let's look at the first 3-second interval to begin with. I have an initial time, a final time, an initial velocity, an initial position, and an acceleration. I can use the second kinematic equation, but written for the x direction. So v final x is equal to v initial x plus the acceleration in the x direction times the delta t, which is only the time interval between 0 and 3 seconds. I have to split this up into pieces. I can't do all 20 seconds at once. I end up with a velocity of 3.6 meters per second, so I know how quickly the cyclist is going at t is equal to 3 seconds and for the next 15 seconds. But one of the things that I need to determine is where the cyclist is relative to their original position. So I'm going to figure out where they are at t is equal to 3 seconds by using the kinematic equation for position. I know x initial is 0. I know v initial x is also 0. But knowing that the acceleration is a positive means that the final position of the cyclist is going to be 5.4 meters ahead of where they were at t is equal to 0 seconds. So I can fill that 5.4 in here, and I essentially know everything I need to know, or I can know, about the first 3 seconds. Now I can switch to the middle part of the story. So maintaining a velocity for 15 additional seconds. That tells me that the acceleration is going to be equal to 0. So if I know the velocity at t is equal to 3 seconds, I also know it's the same velocity at t is equal to 18 seconds. Now, the most interesting thing is to figure out how much distance the cyclist covers over that period. So I'm going to take the final position from the previous step, make that the initial position on this step. At t is equal to 3 seconds, the velocity is 3.6 meters per second. My delta t is 15. And I know that there's no acceleration, so this entire last term is going to cancel out. And I have 5.4 meters plus 54. That's 59.4, so just under 60 meters away from their starting point after 18 seconds of cycling. And then for the last segment, I know the cyclist has to go from 3.6 meters per second to 0. So the acceleration's got to be a negative here. If acceleration and velocity disagree, an object slows down. If they agree, the object speeds up. So I'm looking for disagreement here, or I'm expecting disagreement. I can figure out what that acceleration is just by taking delta v and dividing it by the time interval, where delta v is going to be where the negative comes in because v final is 0, v initial is a positive. And that negative 1.8 meter per second squared acceleration is something I can plug in right here. So it looks like my scan got chopped off a little bit, but there is a square on this term, just like we used in a previous step. So my final position from the last step becomes my initial position for this step, and we end up with 63 meters on the nose. So I don't need to round that any further. It is already at 2 sig figs. Seven is a fun one, similar to one that we solved in class. A loaded cannon is positioned at the edge of the Grand Canyon, which is 1.83 kilometers deep. The cannon is set 45 degrees above horizontal, and the ball exits with an initial velocity of 50 meters per second. A target's placed on the floor of the canyon, 750 meters to the right of the release point, and part A just asks us whether it hits the target or not. So this is phrased as like a yes or no question, but we can answer that simply by figuring out how long that cannonball is going to be in the air. So my coordinate system here has the initial position of the cannonball as 1.83 kilometers. So I can split this velocity vector into an x and a y component because we're given this angle above horizontal. So v initial x is going to be v initial cosine theta. V initial y is going to be v initial sine theta. And it's essentially a moot point here because we're starting off with a 45-degree angle. Our later questions are going to allow us to calculate a different launch angle. But for part A, if I want to figure out where that cannonball lands, I need to know how long it's been in the air. So I've got a final position of 0 meters because I know it hits the bottom of the canyon somewhere. The initial vertical position is positive 1,830 meters, so I needed to convert from kilometers to meters in order to make these units work. V initial y is just V initial times sine 45. And this is something that is happening on Earth. So I know that the the acceleration in the y direction is going to be 9.80 meters per second squared, and it's going to be oriented down. So I have to treat that as a negative here, and I end up with this quadratic equation. I can solve that quadratic for delta t, where delta t is going to be equal to negative b plus or minus the square root of b squared minus 4 times a times c. A being negative means that these two negatives are going to yield a positive ultimately, but I'm going to end up with another negative here in the denominator. And of these two roots, it's the positive one that's meaningful. I know that it doesn't take negative 16.1 second in order for this cannonball to hit the bottom of the canyon. The positive root is the meaningful one, so 23.2669 seconds. The time in the air can't be different for the x direction and the y direction. So I can carry that over to the kinematic equation for position in the y direction now. The cannonball starts at 0 on the x-axis, and my initial velocity, now v initial x, is going to be 50 meters per second times cosine 45. Delta t is known. I could plug that in for delta t in this last term, but I skipped over that because I know that 0 meters per second acceleration in the x direction is going to just cause that last term to drop out. So the actual position where the cannonball strikes the floor of the canyon is 822.609 meters. And we know that our target is 750 meters. So we overshot by 73 meters. So now for part B, let's say we can adjust the initial velocity of this cannon. How do we do that in order to cause the ball to hit the target? We can use the same kinematic equations, one for the x direction, one for the y direction. And in the x direction, it's still true that the acceleration is going to be 0 meters per second squared. It's still true that delta t for the x direction can't be different than delta t for the y direction. But now I don't have an equation that I can solve for delta t directly. So I have two unknowns, in other words. I'm trying to figure out the right initial velocity that would cause the ball to hit the target, but I need to know how long the ball is in the air. So let's call that equation Roman numeral 1. I'm going to write a kinematic equation for position in the y direction, where just like before, I need to treat that acceleration as a negative, just as a consequence of a decision we made further up on our coordinate system. The initial vertical position is 1,830 meters. I have v initial, which is my unknown here. I haven't changed anything about the angle of the cannon, so this is still going to be 45 degrees, just as it was in my x equation. And once again, I have one equation with two unknowns in it. I can call that Roman numeral 2, but because we're trying to figure out the initial velocity in this problem, it makes sense for us to combine 1 and 2 in a way that eliminates delta t. So doing so, I solve equation number 1 for delta t. I plug that into equation number 2. In this middle term here, I have v initial sine 45 times the horizontal range, which is 75 meters, divided by v initial cosine 45. So two things happen here. V initial cancels completely from this middle term, and sine 45 over cosine 45 gives me a tangent. In the last term, I've got 1/2 of the acceleration times the range squared divided by v initial squared times cosine square 45. I'm solving for the v initial that is in the denominator of the third term. Everything else I either know or I can express numerically. So if I plug in some values here, I cancel out my v initials. So I have 1830 meters plus 750 meters times tan 45, which is just going to give me a 1, minus this quantity. It's got some weird intermediate units, but they're going to make sense in a second. Minus 5,512,500 meters cubed per second squared, divided by v initial squared. So I can combine some like terms, I can cross multiply. What I am left with now for v initial is 46.224 meters per second, or 46 to 2 sig figs. So let's try to make sense of this. We know launching at 50 meters per second at a 45-degree angle caused us to overshoot. So if I can't adjust the angle, a smaller initial velocity is what I need in order to actually hit that target at 750 meters. And indeed, we did get one that's slightly smaller, 46 meters per second, as opposed to 50. Here's another interesting take on this. So what if we don't have the ability to change the launch velocity, but I do have the ability to change the launch angle? How do I need to reset that cannon in order to hit the target? My first steps are going to be just like what we did on our previous portion of this, 7b. I can write the equation for position in the x direction. I know the acceleration is a 0, so I can cancel that term out. I know the initial horizontal position xi is also a 0. But again, I end up with an expression that's got two unknowns. I don't know theta, and I don't know delta t. Do the same thing for the y direction, where I've got a negative acceleration, just like we used in our previous two steps. But I end up with Roman numeral 2 being an equation that has two unknowns, theta and also delta t. So if I combine these two to eliminate delta t, I initially end up with 0 meters on the left being equal to 1,830 meters plus v initial sine theta times now the horizontal range 750 meters over 50 meters per second times cosine theta. And something very similar happens in this problem compared to the one that we just solved, because I've got 50 meters per second that cancels. I have a sine theta over a cos theta. That's going to give me a tan theta. And then here in our last term, we have 750 meters squared divided by the quantity 50 meters per second squared. That's going to leave me with negative 1,102.5 meters all over cosine square theta. I'm solving for theta here because I need to figure out what the launch angle is. So I need to make use of the hints that were given right here. So I know 1 plus tan squared theta is secant squared theta. I know secant theta is defined as 1 over cos theta. So let's clean this up a little bit. I have a 1 over cosine squared theta in this term that I can just replace with secant squared theta. And I can replace that secant squared theta with the quantity 1 plus tan squared theta. This is not the type of thing that I would expect you to have committed to memory. If this were to show up on an exam, you would be given that information just as you are here in the practice context. But now I've got a tan theta in the middle term. I have a tan squared theta in the last term. I can solve this quadratic equation. And I'm solving it for tan theta directly this time. I'm going to need to take an inverse tan in order to figure out what the angle should be. But once again, I'm going to get two roots, one negative, one positive. And you can already probably immediately rationalize why that negative root is not going to be meaningful, because that would suggest that when I take that inverse tangent, I would need to set the canon about 28 degrees below horizontal, compared to about 51 degrees above horizontal. So let's think about this. If I know the launch speed is 50 meters per second, and I know setting it to 45 degrees caused us to overshoot a little bit, setting it to a slightly larger launch angle is going to shorten the horizontal range a tiny bit. So a 51 degree angle would also allow us to hit the target without changing the initial velocity. Number 8, a bike tire with a known diameter spins with an initial angular speed that's given in RPM, so revolutions per minute. It's then allowed to decelerate uniformly over a 30-second interval. So first off, for a pebble that's stuck in the tread of that tire, we can figure out what its tangential speed is by determining how to express the angular speed in a more useful unit. So we were given RPM, or revolutions per minute. For part A, we can just do a simple unit conversion using dimensional analysis, because I know 50 revolutions per minute. If I multiply by 2 pi radian for each revolution, if I were to quit right here, I'd be in radian per minute. But I know that each minute has 60 seconds, so everything except for the radian and the second in the statement is going to cancel. Revolutions cancels here, minutes cancel there. And what we end up with is 100 pi over 60, so I can call that 5 pi over 3 radian per second. Or if you want to approximate that as a decimal, that's about 5.2 radian per second. And now that I have that in the appropriate units, I can just go straight to the tangential speed equation to figure out what the tangential speed would be in meters per second for the pebble that's lodged in the treads. I know the diameter of the bike tire, so the radius is what I need to multiply by omega in radian per second. And this combination, radian times meters over second, is just identical to meters per second. So that's where the 1.7 meters per second comes from. And then finally, with part C, we can start to actually take the deceleration into account. We didn't have to think about that at all for the first two parts of this problem. So I know eventually this tire comes to rest. I know it takes 30 seconds to do that. And we've already converted our 50 RPM into something more useful, 5 pi over 3 radian per second. My kinematic equation for this situation is one that looks incredibly similar to our linear kinematic equation for acceleration. The only difference is that now I'm looking at an angular velocity instead of linear ones. So I end up with alpha being a negative, just as it should. It's got value pi over 18 radian per second squared. And if we express that as a decimal, that's 0.17 radian per second squared. But the unrounded value is what you should keep when you are actually plugging stuff into your calculator. Part D, what's the wheel's angular displacement in radian as it's decelerating? Well, I can use the kinematic equation for position, but because I'm tracking something that's moving in a circle, I'm using the rotational version. So theta final is equal to theta initial plus omega initial times delta t plus 1/2 alpha times delta t squared. Instead of getting a linear distance or a linear displacement in meters, we're going to end up with an angular one in radian. So this first term yields 50 times pi. I have 5 times 30 times pi over 3. The second one is going to yield 25 pi, and I'm subtracting this because the acceleration is a negative. So that leaves me with a total delta theta of 25 pi radian. That's approximately 78.5 radian to 2 sig figs, that's 79. Now, once you've got the acceleration, technically your options open up. What we just did is not the only way we can answer this question. We can jump right to our time-independent kinematic equation, which just states that the square of the final angular speed is equal to the square of the initial angular speed plus 2 times the angular acceleration times the angular displacement. I know omega final because I know the bike tire does come to rest eventually. We know its original or its initial angular velocity, and we've got our acceleration from one of the previous calculations. We could solve this for delta theta. And what we end up with here in fraction form, squaring that initial angular speed gives you 25 pi squared over 9. And the units are radian squared per second squared. In the next term, I have a pi over 9 with a negative sign because that has not canceled. I'm still in radian per second squared here, and multiplying that by delta theta will get me into the same units that I have in the first term. That's another way of saying I need to divide in order to figure out what delta theta is. So 25 pi squared over 9 radian squared per second squared multiplied by the reciprocal means I'm multiplying by 9 seconds squared over pi radian. And again, I get that same 25 pi radian, where everything except for 1 radian cancels out. I lose the 9 and the 9 here. I lose one of the pi here, and the other one there. And I come to exactly the same conclusion, 79 radian. That's my angular displacement. So what happens if we stop the wheel, restart it, and give it a different tangential speed, and you count the number of revolutions? It decelerates uniformly, so I know eventually it's going to come to rest. I don't initially know how much time it's taken to come to rest. So first off, it's not reasonable to assume that the acceleration in this case will be identical to the acceleration that we used earlier. So let's figure out what that must be by taking that tangential speed and the radius, which we were given further up, to figure out what omega initial is. And what we get here is 11.51 repeating radian per second. In this scenario, we counted the number of revolutions, not the number of radian. So I need to figure out how to convert that from revolutions to radian. And it's nice and simple because each revolution is 2 pi radian. So this becomes 64 pi radian, which is a little over 200 radian. And now I need to figure out what alpha is, so the angular acceleration, without knowing anything about the time. And here's another scenario where the third kinematic equation that's time independent is a great choice. I know eventually it comes to rest. I know how quickly it was moving when it began decelerating. And I know that it takes 32 revolutions, so 64 pi radian. I can solve this for alpha. And when I do so, I get a negative, just as I would expect, because the wheel's not speeding up, so it's slowing down. This value is about 0.3297 radian per second squared. Now I can plug that into another kinematic equation. And technically, you could have used the first one, so the one that we also used in step D of the previous problem. And we could solve that for delta t, but that's not our best idea because that would require using the quadratic formula. Instead, we can just go straight to the simpler one. The final angular velocity is the initial angular velocity plus the angular acceleration times delta t. Solving that for delta t gives 34.921 seconds, so 35 seconds. And if we compare that to our original example, when we had a tangential speed that was only about 1.7 meters per second, it only took about 30 seconds for that wheel to come to rest. We give it more or a greater tangential speed for step E, so 3.8 meters per second. It follows that it should take more time for that same wheel to decelerate to rest compared to when it was moving with a smaller tangential speed. Is a relative velocity problem. A camper wants to paddle their canoe across a river that's 50 meters wide. The river flows 1.0 meter per second east relative to Earth. The canoe moves 1.5 meters per second relative to Earth. And we can see here in our diagram, the canoe is angled with respect to this dashed line. So that's just the line directly across the river. So in essence, we know that the paddler or the camper here is trying to account for the river's motion so that they can control exactly where they end up. Okay, so first off, let's take what we know about the velocities that we were given. 1.0 meters per second relative to Earth. So that's RE for river relative to Earth. If that's positive 1.0 meter per second, I know I can flip to the other reference frame and say that the velocity of Earth relative to the river is just negative 1 meter per second. And with the canoe, we've got its velocity relative to Earth. So VCE, if that's a positive, 1.5 meter per second, I know VEC is going to be negative 1.5 meters per second. And the fact that the canoe is angled backwards here or into quadrant number 2, that's not going to have an impact on how I can invert my reference frames when I flip from canoe relative to Earth and then Earth relative to the canoe. What it does mean is that I need the sine component of V canoe to perfectly cancel out V river. That's the only way that you're going to land directly across the river. So VCE sine theta is what you get when you break this canoe vector down into an x and a y component. So I need that magnitude to be the same as the river velocity's magnitude, and I can use that to figure out what theta is, so how far you would have to angle your boat or your canoe in order to land directly across the river, instead of being swept along with the river. Part B, what is VCR, the velocity of the canoe relative to the river? There's a little right triangle here that shows what we are going for in this problem. So we need the river's velocity to be perfectly canceled out by one piece of the canoe's velocity relative to Earth. Now that I know this angle theta, I've got some wiggle room. I've got two different ways I can confirm that VCR, the canoe relative to the river, is just 1.1 meter per second. One would be to recognize that VCR has to have the same magnitude as the velocity of the canoe relative to Earth times cosine theta. So I'm grabbing the adjacent piece this time. That gives me something that rounds to 1.1 meter per second. However, it's also completely valid to come at this from a Pythagorean theorem perspective. I know the magnitude of the velocity along the hypotenuse and the magnitude of the velocity in the x direction. So from east to west, in other words. The magnitude of that third component is just going to be the square root of 1.5 meters per second quantity squared minus 1.0 meter per second quantity squared. And you get the same value here. So 1.1 meter per second. That means that the canoe is moving relative to Earth faster than it's moving relative to the water. And then finally, for part C, how long does this trip take? Well, just like a projectile motion problem, the delta t for the x direction can't be any different than the delta t for the y direction. And in this case here, we're kind of forcing our delta x to be equal to 0. So we don't want the canoe to drift along with the river. We want it to land directly across the river. So delta y is what we need to work with here because we know the river's width is 50 meters. We know that the velocity in the y direction is literally the same as what we called VCR. Those magnitudes describe exactly the same property of this problem. I can solve that for delta t, and you end up with 44.721 seconds. So to the appropriate number of sig figs, that's 45 seconds. So let's try something different. If instead our camper launches perpendicular to the southern bank, how far downstream will they be when they get to the other side? V canoe relative to Earth, now this is angled just straight toward the northern bank. So there's no attempt to counteract the motion of the river. They're just allowing the river to take them further downstream. I just copied down the same information about the velocity of the river relative to Earth and Earth relative to the river, and the velocity of the canoe relative to Earth, and then Earth relative to the canoe. But what we're actually looking for here is essentially what we started with in our previous problem, but we're going to allow this angle theta to approach 0. So we'll end up with a degenerate right triangle that's got this angle theta being equal to 0. So that means that this negative VR relative to Earth, that's going to go to 0 because you're no longer trying to fight against the river. What does that mean? That means that VCE sine theta is going to go to VCR, which is going to go to 0. VE cosine theta, now that's going to approach VCE, which we know is 1.5 meters per second. So again, we're just dealing with a bunch of constant velocities. So I'm going to use the kinematic equation for constant velocity, and I'm going to just subtract S initial from each side. So I just have a delta S being equal to the magnitude VCE times delta T. I know the magnitude VCE because that was given to us beforehand, and it's the same river. So 1.5 meters per second. I can solve this for delta t. I get an amount of time that's less than what we saw before. So what this tells us is that counteracting the flow of the river is going to cost you some time, but it's going to control where you land on the other side of the river. And then finally, we're actually trying to figure out how far horizontally our canoe moves over the course of this problem. So I can use the same expression now for the x direction. The velocity of the river is all that's responsible for carrying the canoe along the east-west axis. So I can take that velocity, multiply it by the time we just found, and I end up with a 33-meter drift. Next, what if we launch the canoe at a 45-degree angle, and we launch it so that the canoe is at least partially working with the river? If that canoe ends up 80 meters downstream from the launch position, we can calculate the time, the velocity of the canoe relative to Earth, because that's going to be different in this case because the river is helping, not hurting. And then VCR, the velocity of the canoe relative to the river. So now the only relevant piece of information to carry over from the first two parts is the same as what we used in our previous part, the velocity of the river relative to Earth and Earth relative to the river. I have two displacements though, but I do know that the canoe can only be moving along the x-axis for the same amount of time that it moves along the y-axis because the trip ends when the canoe goes from the southern bank to the northern bank. So we know that delta x, just in general, is going to be the magnitude of the velocity in the x direction times delta t. And we can look to our diagram to figure out what the velocity in the x direction is going to be, because the river is carrying the canoe downstream, but the canoe itself has a component of its velocity that's also oriented downstream. So I need to add those together. So VCE sine theta plus the river's behavior times delta t, that's got to equal 80 meters. And I've got two unknowns here. VCE is ultimately what I'm trying to find. Delta t is an unknown. If I switch to the y direction, now I can grab the cosine component of VCE, but the river isn't flowing north or south, so it's not helping or hurting in this direction. That means that Vy is just VCE cosine theta. And I have two equations, Roman numeral 1 and 2. I can solve this system to eliminate VCE first, because we're trying to find the time. So I can solve each one for VCE. I can set those equal to one another. I notice I only have one unknown at this point, which is delta t. So I can solve for it, and we get 30 meters per second. Once I have that, I can go back to either of my original equations and just plug that delta t in so I can solve for VCE. And because I have two options, but they are both representing the same scenario, I can't get two different answers, but I can demonstrate that I get the same answer twice. And when we apply sig figs appropriately, that becomes 2.4 meters per second. And the last thing we're trying to find is VCR, the velocity of the canoe relative to the river, so literally the water, not the riverbank. If I look at my right triangle, I know VCE makes up the hypotenuse, and we committed to a 45-degree launch angle here, so I know that's 45. But I know I can say VCR added to VRE is equal to VCE. This is that trick that we used where the middle subscripts cancel out when you arrange them in this way. So to figure out what VCR is, again, I could just use the Pythagorean theorem. So the square of 2.357 meters per second minus the square of the river's velocity relative to Earth, 1.0 meter per second, quantity squared, that leaves me with 2.1 meters per second. So the fact that the river is flowing with the canoe means that the velocity of the canoe relative to Earth is bigger now than we saw in any of our other examples. and the velocity of the canoe relative to the river water is not zero like it was in our previous example. It's also not just equal to the river's velocity in the opposite direction. Here, it's now slightly larger, 2.1 meters per second. And then our last practice problems, we have a block that's on a frictionless ramp. The ramp is made out of a 2.0, and I don't know anything about the mass of the block or the size or anything like that, but I do know that it takes 0.85 seconds to go from the top to the bottom. So this is an example of a case where we can take the free fall acceleration vector and then break it up into one parallel piece and one perpendicular piece, where the perpendicular piece is not going to give us anything that's helpful here, but I know its magnitude is just going to be g cosine theta. The one that's going to help us out on this problem is a parallel. So that's g times the sine of theta. And if I choose the s-axis just to be the surface of the ramp, I don't have to bother with tracking how that block moves vertically while it's simultaneously moving horizontally. I can just make s forward, in essence. And that means that the acceleration that we called a parallel is also going to be the acceleration in the s direction. So I don't know what the angle is yet, but I can use the fact that I know the distance traveled is 2 meters and the time is 0.85 seconds to figure out what that angle theta must be. So I start with the first kinematic equation. Our block is just placed at the top of the ramp, and I've chosen to put the origin there so I can plug in a 0 here. The block isn't pushed, it's just set on the top of the ramp and it slides down, so I know v initial s is equal to 0. And I can rearrange what I have left over to figure out that sine theta is equal to 0.56493. And there are no units here, but when I plug this in, if I take an inverse sine, I'm going to end up with an angle of 34.398 degrees. Applying sig figs takes us to 34 degrees. And it's worth commenting on here, I don't think I mentioned this earlier, we know free fall acceleration to 3 sig figs, that's what our baseline value is going to be. But since our time and our distances are only known to 2 sig figs, this still does round down to 34. And then for part B, how quickly is it moving when it gets to the bottom of the ramp? Well, I know the angle, I know delta t, I know v initial. I have a couple of different ways I can figure out what v final is. One involves using the time-dependent equation for velocity. So plugging in a 0 for v initial and then using g times sine 34.398 for the acceleration in the s direction. That gives me a final velocity that rounds to 4.7 meters per second. And as a check, we can do the same process, but with our time-independent kinematic equation. So we can take the fact that the block experienced a displacement of positive 2 meters, and then we can use that to solve for v final s, and we get exactly the same number. So 4.7 meters per second, 2 separate times. And then finally here at the end, what if the same board is repositioned so that it's at a 20-degree angle with respect to horizontal? And we push the block from the bottom of the ramp to the top, but we give it a quick jolt that is just enough to get it to go to the top of the ramp. What's the initial velocity and how much time does it take for this to happen? This is almost exactly the same as the way we broke our free fall acceleration vector down in number 12. The difference here is that now Earth is working against that block. It's not trying to accelerate it as it goes toward the top. It's trying to decelerate it as it goes toward the top of the ramp. So I need to be really explicit about the coordinate system. I'm still going to say that forward is positive for the s-axis. That means that the acceleration in the s direction points the opposite way. I have to treat that as a negative when I do that. And because I don't have information about the time just yet, I'm going to use the kinematic equation that is time independent so that I can take the 20-degree angle, I can take free fall acceleration, and I can take the length of the ramp. with the knowledge that eventually it comes to rest, to figure out what V initial must be. So 3.6616 meters per second, that rounds to 3.7 meters per second when we apply sig figs. And then to figure out the time, technically I could use the kinematic equation for position, so the same one that we used in the first step of our previous problem, but I'd have to solve for delta t using the quadratic formula. Instead, a simpler way to get at the same information is to use the velocity equation. So v final in the s direction is equal to v initial in the s direction plus the acceleration in the s direction times our delta t. Acceleration's got to be treated as a negative, which makes sense because when I subtract both sides of this equation by 3.6616 meters per second, I get a negative on the top and a negative on the bottom, so a positive delta t. And when we apply sig figs, that is simply 1.1 second.